sklearn, cross-decomposition, PLS regression. Description: PLS regression is a supervised dimensionality reduction technique that finds latent variables, components in both the predictor X and response Y variables, aiming to explain the maximum covariance between them. It differs from principal component regression PCR by using the information from both X and Y for component extraction, leading to better prediction when the variables are highly correlated. Inputs: X a 2D array of predictor variables, N samples, X n features. Y a 2D array of response variables, N samples, X n targets. Outputs: YPRED the predicted response values based on the fitted model. XCOS the scores of the predictor variables on the latent variables N samples X n components. YSCOS the scores of the response variables on the latent variables N samples X n components. COA the coefficients of the linear model that relates the latent variables to the response variables. Steps: calculate the covariance matrix between X and Y. Find the singular value decomposition SVD of the covariance matrix. Extract the top n components' singular values and their corresponding vectors. Project both X and Y onto the subspace spanned by the extracted singular vectors, resulting in the XCOS and YSCOS. Fit a linear model using the XCOS to predict the YSCOS. Metrics: R squared R2 represents the proportion of variance in the response variables explained by the model. Mean squared error MSE measures the average squared difference between the predicted and actual response values. Root mean squared error RMSE the square root of MSE, providing an interpretable scale for the error. Visualization plots: scatterplots of XCOS vs YSCOS to visualize the relationship between the latent variables. Scree plots showing the singular values, indicating the importance of each component. Fine-tune parameters: N components the number of latent variables to extract. Determining the dimensionality reduction. Scale whether to scale the data before performing PLS. Influencing the impact of variable scales on the results. Copy whether to copy the data before fitting. Allowing for in-place modification of the original data. Maxiter maximum number of iterations for the PLS algorithm. Uncertainty methods. Bootstrapping resampling the data with replacement to estimate the variability of model. Parameters and predictions. Cross-validation splitting the data into multiple folds and training the model on different combinations of folds to assess its generalization performance. Challenges and fixes. Challenge 1: multicollinearity in predictor variables can lead to unstable PLS results. Sample use case that resulted in challenge 1: when predictors are highly correlated, the PLS model may overfit the data and perform poorly on unseen samples. Fixes to challenge 1. Use variable selection techniques to remove redundant predictors. Regularize the PLS model with methods like ridge regression. Challenge 2: choosing the optimal number of components can be subjective. Sample use case that resulted in challenge 2: selecting too many components can lead to overfitting, while selecting too few can result in underfitting. Fixes to challenge 2. Use cross-validation to evaluate the model performance with different numbers of components. Examine the Scree plot for an elbow point, indicating a good trade-off between dimensionality reduction and explained variance.